Jai Hind students, welcome to my YouTube channel. Students, find confidence within your heart and let it be your guide. Strive even harder toward your dreams and they won't be denied. So with that students, let's start today's session. In the previous lecture, we have discussed about Ampere's circuital law. Today, we will start with the applications of Ampere's circuital law. So we will first try to find out the expression for the electric field at a point due to a current carrying long straight solenoid. Now solenoid means it's like this. This is a long solenoid and number of turns of copper wire or any conducting wire is wound over it like this. These are the number of turns of copper wire wound over here. Let us consider capital N with the number of turns and the length of this long solenoid will be capital L. Okay, let's consider L with the length of the solenoid and capital N with the total number of turns. Then number of turns per unit length, it would be small n, it's equal to N by L. So small n is the number of turns per unit length, right? N is the total number of turns, L is the length of the long solenoid under consideration. So these are the number of turns of any conducting wire. Now suppose the current is flowing in the clockwise direction when you see from this end, right? So suppose this is the current carrying conductor. Now as we are aware students, this is a solenoid and through this phase it will appear as if the current is flowing in the clockwise direction. So this phase will act as the south pole while the other phase through which the current will appear to be flowing in the anti-clockwise direction will behave as the north pole. We are already aware students, a current carrying coil behave as a magnet. One face of it will behave as the south pole while the other face of it will behave as the north pole. So the current carrying solenoid will also behave as a bar magnet, right? We are already clear with this topic. This is a current carrying loop. If the current appears to be flowing in this loop in the clockwise direction, then this face of the loop will behave as south pole, where the magnetic field lines seem to enter. It will be perpendicular to the plane and directed inwards, isn't it? While on the other hand, the other face of the same loop through which the current appears to be flowing in the anti-clockwise direction, that face of the loop will behave as the north pole, like this. From this face, it will appear as if the field lines are coming out. So it will act as a north pole. And magnetic field lines, you are aware students, inside a magnet, inside the body of the magnet, the field lines are directed from south to north. While outside the body of the magnet, it is directed from north to south. So it is in the form of continuous closed loops. It's like this. Suppose this is a magnet. This is south and this is north. These are the two poles where the magnetic force of attraction is maximum, right? Inside, the field lines are from south to north. Outside, it is from north to south. It's like this. These are the field lines. So inside, it's from south to north. And outside the body of the magnet, the field lines are directed from north to south. These are the field lines. So, the end of the solenoid through which the current appears to be flowing in the clockwise direction, that will behave as the south, while the face or the end of the solenoid through which current appears to be flowing in the anti-clockwise direction, that will behave as the north pole, right? So, this end will behave as south, while this end of this solenoid, current carrying solenoid, will behave as the north pole, right? So therefore, this current carrying solenoid does behave as a magnet. One end behaving as south pole, the other end behaving as north pole. Clear? So if you draw magnetic field lines over here, just like as we have drawn in the case of a bar magnet, it will be like this. Inside, it will be from south to north. And in case it is a long straight solenoid, then the magnetic fields inside the solenoid are almost perfectly parallel and equal spaced, right? And outside the body of the magnet, it will be like this, from north to south. Don't forget to indicate the direction, right? It should be like this. These are the magnetic field lines. Inside the body of the magnet or the current carrying solenoid, the field lines are directed from south to north, and outside it will be directed from north to south. These are the field lines. Clear, students? This is south, and this one will act as the north pole. This is it. So these are the field lines. Clear? So 2-3 points can be easily concluded. First, a current carrying solenoid behave as a bar magnet. One end of the current carrying solenoid will behave as the south pole, while the other end of the solenoid will behave as the north pole. Second point, students. Inside the solenoid, the field lines are almost straight and parallel, which suggests that magnetic field at any point inside the long current carrying solenoid is constant, right? So this is very important point. First is current carrying solenoid acts as a magnet, right? This is first point. Second point is inside magnetic field inside the current carrying solenoid is constant. As you can refer to this diagram, the field lines inside the long solenoid are almost straight and parallel. It is like this. And whenever field lines are represented by equidistant parallel lines, it represents that the magnetic field in this region must be constant. So the magnetic field inside the solenoid is constant, right? Third point, students. In case of a long current carrying solenoid, the magnetic field in this region A or in this region B. Here, look, there are no field lines. Therefore, just outside the current carrying solenoid, the magnetic field is 0. Here, the magnetic field is 0. So, just outside the magnetic field due to a current carrying solenoid is 0. So, in this region, in these regions A and B, the magnetic field is 0. Because there are no field lines. Absence of field lines represents 0 magnetic field or negligible magnetic field. Clear, students? Fourth point. At the end points, students, these are the end points. At the end points, we can resolve the field line into two components. So the contribution to horizontal as well as vertical would be half. That is, what I mean to say is that at the end points, the magnetic field is half the magnetic field inside the current carrying solenoid. So these are four very, very important points which we need to remember, right? I repeat, students. A current carrying solenoid behave as a bar magnet. One end of it behave as the south while the other end behave as the north, right? The end of the solenoid through which current appears to be flowing in the clockwise direction, that will behave as the south pole, right? While the other end of the solenoid through which the current appears to be flowing in the anti-clockwise direction, that will behave as the north pole, right? This is the first point. Second, magnetic field inside the long solenoid, they are almost straight, parallel, equidistant. Magnetic field lines which are straight, equidistant and parallel represents uniform magnetic field. So, magnetic field at any point inside the long current carrying solenoid is constant. Third, just outside the current carrying solenoid there are no magnetic field lines, indicating that magnetic field is 0. It is actually valid for long current carrying solenoid, right? Fourth one, at the end points, these are the end points, students. These are the end points. At the end points, the strength of the magnetic field will get reduced. It will bend like this. So, it won't be perfectly horizontal nor it will be perfectly vertical. So, at the end points, the field strength, it is found to be equal to half the field strength at any point inside the solenoid, right? So, let's come into the derivation part. Let's proceed towards the derivation part, where we will try to find out the expression for the magnetic field at a point well inside the current carrying solenoid using Ampere's circuital law, right? So let's proceed towards that section. So Ampere's circuit law, students, we all are aware, it is applicable for any closed loop, isn't it? The closed line integral of a magnetic field is numerically equal to mu naught times, which is the absolute permeability of free space, times the net current threading through the loop. So this is the statement of Ampere's circuital law. So we'll be making use of this particular law so as to find out the expression for the magnetic field, right? So what to do is, let's draw the diagram over here. This is a long solenoid under consideration, right? As we have considered, its length is L and number of turns is capital N. So small n is the number of turns per unit length. So what will be the SI unit of N? It will be meter inverse, right? Small n is the number of turns per unit length. These are the number of turns of the copper wire or any conducting wire, which is considered to be capital N. So a conducting wire is wound over its length like this. This is the current. So as we have discussed, this end of the solenoid through which current happens to be flowing in the clockwise direction will act as the south, while the other end will act as the north polarity, right? So we need to find out the expression for the magnetic field at a point well inside it. Now in order to apply Ampere's circuit law, we need to consider any closed loop. Here what we do is, let's consider a rectangular loop. This is an imaginary loop, that is why I am representing it with the help of dotted lines. Suppose this is an imaginary loop. We are considering a rectangular loop of length L, right? Suppose it is A, this is B, this is C, and this is D. So students, this is an imaginary rectangular loop as drawn in the diagram of length capital L, right? Now, in this closed loop, let's apply Ampere's circuit law. So, as per Ampere's circuital law, what we get is closed line integral of the magnetic field is equal to mu naught times. Mu naught is the absolute permeability of free space. We are considering inside to be free space or vacuum. No medium is inserted, right? Mu naught times the net current threading through the loop. This is the loop. How many times current is threading through the loop? 1 time, 2 time, 3 time, 4 time, 5 time. The number of turns. That is n times current is threading through this loop. So here net current threading through the loop is Ni. Current is threading through the loop n times. And as per Ampere's circuit law, the right hand side is mu naught times the net current threading through the loop. So it will be mu naught Ni. Capital N is the number of turns, right? So let's evaluate it. It can be expanded, it can be split into 4 parts. This is closed line integral, isn't it? We'll split up into 4 parts. A to B, B vector dot dl vector, plus B to C, B vector dot dl vector, plus C to D, B vector dot dl vector, plus D to A. So this will complete the loop, B vector dot dl vector, and it is equal to mu naught Ni. Capital N may be written as small n into L into pi. It's clear, students? Simply I have expanded this into 4 integrands, right? Let's concentrate on this. Here, as stated, magnetic field is directed along this direction. Just now I have convinced you. And I told you in my previous lecture, this is the length of the elementary portion dl. And wherever possible, it is to be measured along the direction of the magnetic field. So A to B. So dl is also measured along this direction. So what's the angle between B vector and dl vector? It is 0 degree, right? So it will be B dl cos 0, right? What about this? B vector dot dl vector. This is the elementary portion, right? B to C. This is the direction of dl vector and this is the direction of magnetic field. So what's the angle? 90 degree. This dot or the scalar product of two perpendicular vectors is always 0. So this will not contribute anything. Plus C to D. C to D. Here students, we have already decided. Here just outside the magnetic field is 0. Just outside the current carrying solenoid, there are no magnetic field lines. The magnetic field lines will be like this, south to north, and outside it will be from north to south, like this. Inside south to north and outside it will be from north to south. So just outside the current carrying solenoid, due to the absence of any magnetic field lines, we can safely conclude that the magnetic field just outside is 0. Therefore, since magnetic field is 0 over here, so this will also not contribute anything. Plus, consider this one, D2A. Here again, dl vector is directed along this and field line will be directed along this. So the angle between them is 90 degree. So scalar product of two perpendicular vectors is 0, cos 90 being 0. So it will be mu naught n L I. Clear students? So we are left with only this one. Cos 0 students, we are aware it's equal to 1. B is the magnetic field which I have stated inside the current carrying solenoid. Magnetic field lines are almost straight, parallel and equidistant. So magnetic field inside is constant. So therefore, B being constant, it can be taken outside the integration, right? What about integration of dl? Cos 0 is 1. What about integration of dl? If you integrate the small elementary portions from A to B, that will give you the total length of A to B of the loop. And length of AB portion is capital L. Cos 0 is 1. So it will be mu naught n L I. L will get cancelled. So magnetic field at a point inside a current carrying solenoid is n mu naught I. So students, this is the expression for the magnetic field at a point inside a current carrying straight solenoid. Clear students? Now we will discuss some special cases. Okay, first case. Look students, just outside that we are aware, the magnetic field is 0. That we are already aware. Second is at the end points. We have discussed magnetic field is half of the strength of the magnetic field which is inside the current carrying solenoid. So in this case it will be half n mu naught I. Right? Third, suppose the space is filled with some medium, or you can say some rod of say material of permeability mu is inserted as a core, right? Then the magnetic field at a point inside the current carrying solenoid will be given by n in place of mu naught. This signifies absolute permeability of free space. Now when a rod is inserted, say of material having permeability mu, then instead of mu naught we will write here as mu. Mu is the absolute permeability of the medium, of the material of the rod which is inserted as a core, right? And students, as this is relative magnetic permeability, it is mu by mu naught. Just like relative permittivity, it is defined as the ratio of the absolute permittivity of the medium to the absolute permittivity of free space. Similarly, in magnetism, we define relative permeability. It is defined as the ratio of absolute permeability of the medium to the absolute permeability of free space. So in place of mu, you can write mu r into mu naught. Therefore, magnetic field at a point well inside a current carrying long solenoid in which a rod of material of permeability mu is inserted is given by n. In place of mu, you can write mu naught mu r I. So students, this is the formula, right? So these are the special cases which are associated with the long current carrying solenoid. So students, I hope you have understood this first application. So students, we are done with the first application of Ampere's circuit law, which is to find out the expression for the magnetic field due to a long straight current carrying solenoid. Right? Now what we'll do is, we'll discuss the second application of Ampere's circuit law, which is determination of magnetic field due to a current carrying toroidal solenoid. Now toroidal, the term toroidal, it contains the root torus, T-O-R-U-S, torus. It stands for anchor, ring. It is torus, T-O-R-U-S. It stands for anchor, ring. Anchor means some supporting ring. So this is the ring I am talking about. It's a supporting ring. And over this supporting anchoring ring, number of turns of conducting or copper wire is wound like this. So it is like this. These are the number of turns of conducting wire which is wound over this supporting ring. So that will become a toroidal solenoid. This will become a toroidal solenoid. So suppose current enters along this direction, so current will leave along this direction. Clear, students? So this is a toroidal solenoid. Now students, imagine a toroidal solenoid to be of extremely large radius. Extremely large radius. Again I repeat, if we consider a toroidal solenoid of extremely large radius, then a small portion of a large toroidal solenoid will behave as a straight solenoid. Right? So let's consider this to be the center. And let us consider R to be the radius of the ring. R may be considered to be the mean radius, right? This may be considered the inner radius, this may be considered to be the outer radius. So R, which is the mean radius, it can be considered to be Ri plus Ro divided by 2. So if in any numerical or article, if Ri, Ro are given, Ri is the inner radius, this one Ri, it is the inner radius, and R0, this is the outer radius. Then the mean radius would be given by Ri plus R0 divided by 2, right? And here, let's consider n be the total number of turns. N be the total number of turns. Then students, the number of turns per unit length, which we have denoted by small letter n, that is number of turns per unit length. It is small n. It is total number of turns is n divided by total length of the toroidal solenoid of radius r. That will be the circumference, that is 2 pi r. Right? Put this as equation number 1. So the difference in the straight solenoid and the toroidal solenoid is that in the previous case where we have considered a straight solenoid, there the number of turns per unit length is capital N divided by L, linear length. Here the number of turns per unit length is capital N divided by total length, right, which will be in this case the circumference, which is 2 pi r. Again, SI unit of small n would be per meter, right? Okay, now let's draw the field lines. Now here, if the current flows in a particular direction, what happens is magnetic field lines will enter through one face and it will leave the other face. So for each loop, if you draw the magnetic field lines, it will enter one face while it will make an exit from the other face. So what I mean to say is that if you complete the diagram, the field lines will be like this, which is represented by dotted lines. These are the field lines. So field lines will tend to remain confined within the solenoid. It will tend to remain confined within the solenoid. It's like this, as shown in the figure. It will tend to remain confined within the solenoid. Through one face of the loop, the field lines will seem to enter, and through the other face of the same loop, the field line will appear to come out of that loop. So as a result, the field lines will be as shown in the diagram. So field lines will remain confined within the solenoid, right? So here there are no magnetic field lines, it is the region bounded by the solenoid, and this is the outside region. So here magnetic field is 0, here magnetic field is 0. So students, this is very important point. The magnetic field lines inside a current carrying toroidal solenoid remain confined within the solenoid. Thus, the region enclosed by the solenoid, here the magnetic field will be 0. And outside the toroidal solenoid, here there are no magnetic field lines. Here also the magnetic field line is, or magnetic field is 0. So magnetic field will be only within the current carrying toroidal solenoid. And here also you can see the field lines are parallel to each other. Therefore, the magnetic field strength at any point inside the toroidal solenoid may be considered to be constant, right? So these are the points. B inside the bounded region. This is the bounded region, 1, right? So first portion, it is equal to 0. B outside, this is suppose the second region, it is also 0. And magnetic field at any point inside, like here, this one, this is magnetic field, this is region 3. Suppose we consider this to be region 3 inside. So magnetic field in the region 3, it will be equal to constant. And we are going to find the expression for this magnetic field by making use of Ampere's circuit law. So that's our objective, right? So I hope you have understood this concept, isn't it? Okay students. Now, as I've told you, in order to apply Ampere's circuit law, we need to imagine or we need to consider some closed loop. Here, taking point O as center and maybe R as radius, we'll consider a circular imaginary loop, right? So, this is the loop. Suppose this is the loop I am considering. This is an imaginary loop in which Ampere's circuit law will be applied, and this loop is considered to be same as that of the mean radius of the toroidal solenoid. This is the loop under consideration. Because in order to apply Ampere's circuit law, the imaginary loop is absolutely compulsory, right? So, applying Ampere's circuital law, we get closed line integral of the magnetic field is equal to mu naught times the net current threading through the loop. Look students, this is the loop. This is the imaginary loop of radius r, right? From this loop, how many times the current is threading? So this is 1 time, 2 times, 3 times. So how many times the current is threading through the circular loop? It will be equal to the number of turns, that is capital N. So here, the net current threading through the loop would be N into I. Capital N is the number of turns, right students? Okay. Magnetic field, as I have stated, you can consider any point over here. Magnetic field, it's parallel like this, it's along this direction, right? At any point it will be given by drawing a tangent. DL, it's the length of the elementary portion. It is to be measured wherever possible along the direction of the magnetic field, and since it is circular, therefore the direction again is given by drawing a tangent like this. So what is the angle between magnetic field and DL vector? It's 0. So what do we get is B, this is scalar product, the magnitude of B, magnitude of DL, cosine of the angle between these two, which is 0, it's equal to mu naught. In place of capital N, we can substitute as N times 2 pi r multiplied by r. Clear students? Cos 0 is 1. Also, magnetic field at any point inside the current carrying toroidal solenoid is constant. Why? Because magnetic field lines are almost parallel inside the toroidal solenoid. So magnetic field being constant, it can be taken outside the integration. So integration of dl is equal to n mu naught 2 pi r into I. Clear? Now what is integration of dl? If we join the small elementary portion of the circular loop, that will give us the total circumference of the imaginary circular loop under consideration. And this imaginary loop, circular loop, is considered to be of radius r. So total length of that loop would be 2 pi r. So what we get is b multiplied by 2 pi r is equal to n mu naught 2 pi r I. 2 pi r get cancelled. So what we get is magnetic field is equal to n mu naught I. So students, we obtained exactly the same expression as was obtained in the case of a long straight current carrying solenoid, with the only difference being small n over there is capital N divided by L, number of turns per unit length, linear length. Here small n is the number of turns per unit circumference of the loop, that is 2 pi r. Clear? Rest everything will remain same. And I have justified it theoretically as well. If you consider a toroidal solenoid of extremely large radius, then a small portion of this toroidal solenoid will act as a straight solenoid only. So the formula will remain same, n mu naught I, isn't it? N is the number of turns per unit length. And as students, we have discussed, in case a material maybe of permeability mu is inserted inside this core, right, in place of air or vacuum, then the expression becomes, in case of any medium, then it will become n mu I. This will be the absolute permeability of the material of the medium under consideration, right? And as I have stated, mu r is mu divided by mu naught. This is relative permeability, which is defined as the ratio of the magnetic permeability of the medium to the absolute permeability of free space. So this expression can be written in terms of relative magnetic permeability as well. So what we get is, it will be equal to n, this is mu naught, mu r, this is the relative permeability, and I. So this is the expression, students. So I hope you have understood the first two applications of Ampere's circuit law. These two are very, very important topics, right? There is third application as well, which we will be discussing in the next lecture. So do join me then. Till then, do take care and stay blessed. Thank you.